Hello, good day everyone. So we will now continue the discussion on trigonometric equations. This time around, we will talk about the second method on how we can solve them. Just a recall, when we are solving trigonometric equations, usually we wish to get or obtain the fundamental solution set or FSS. These are solutions that we found or that we can find within the first rotation along our Cartesian plane. So basically, all solutions from 0 to 2 pi belongs to the fundamental solution set. So we now proceed with the second solving tip. So we use this tip whenever we have equations containing a single trigonometric function with different arguments. When we say different arguments, they have different angles involved. Or if we have more than one trigonometric functions in our equation. In this case, we use trigonometric identities to express the equation to a single trigonometric function or factors of different trigonometric functions. We then apply solving tip number 1 after simplifying. To further explain how solving tip number 2 works, let's have this example. So for the fundamental solution set of the equation, cosine x minus sine 2x equals 0. So if you notice from our equation, we have two trigonometric functions involved. We have cosine and sine, and we also have two different arguments, x for cosine and 2x for sine. So in order to solve this, take note that we have an expression that is equivalent to sine 2x using our double angle identity. And with that, we know that sine 2x is just the same as 2 sine x cosine x. So we replace sine 2x with that identity. So we now have cosine x minus 2 sine x cosine x equals 0. Now, if we look at the left-hand side of our equation, we have two terms, cosine x and 2 sine x cosine x. Here, notice that both terms have cosine x as a factor. So what we do is to factor out cosine x, and if we do that, factoring out cosine x here on the first term, we'll be left with 1, and then factoring out cosine x to 2 sine x cosine x, we will be left with 2 sine x. And take note, if we are multiplying two expressions and the answer is 0, then that means either one or both are expressions or factors in this case must be 0. So that means that cosine x here must be equal to 0, or the other factor, 1 minus 2 sine x, must be equal to 0. So now we have two equations having a single trigonometric function each. So what we'll do is to solve each equation. So let's look at the solution first for cosine x equals 0. So again, cosine is equal to 0 whenever we are in the y-axis, whether on the positive y or on the negative y-axis. So the values of x that will make cosine x equal to 0 are pi over 2 or 3 pi over 2. Next, if we have 1 minus 2 sine x equals 0, so take note, we first simplify this one. We segregate or we isolate sine x. So we add negative 1 to both sides. So we will get negative 2. Sine x equals negative 1. And then we divide both sides by negative 2. That's why we have sine x equals 1 half. But take note, 1 half is greater than 0, meaning sine is positive. And we know that sine is positive in the first and in the second quadrant. So for the first quadrant, sine is equal to 1/2 whenever x is pi over 6. And then for the second quadrant, we just need to get, or we just need to solve, no, for the value of x. Since we're in the second quadrant, that will be pi minus the reference angle. Our reference angle is pi over 6. So we have pi minus pi over 6. We get 5 pi over 6. So that means that our fundamental solution set contains the elements pi over 6, pi over 2, 5 pi over 6, and 3 pi over 2 in ascending order. All right? So now let's try to, before we proceed to example 6, let's go back first to um, example 5. So if we are asked for the solution set, all we need to do again is to add 2 pi n to each element of the FSS and then add the condition that n is an integer. Okay, let's proceed to example 6. Solve for the fundamental solution set of 2 tangent squared x plus secant squared x equals 2. So here we have, again, two different trigonometric functions involved. We have tangent and secant. So in order to solve this, we have to either change your tangent into secant or your secant into tangent. So for this solution, we are going to change secant into tangent. And using our Pythagorean identity, we know that secant squared x is equal to tangent squared x plus 1. So we just replace secant squared x by tangent squared x plus 1. And then right after, we now combine like terms. So we have here 2 tangent squared x plus tangent squared x. So that is 3 tangent squared x. And then we have 1 here. We add negative 1 to both sides. So we're going to, the 1 here on the left side will be canceled out. And then 2 minus 1, we get 1. And then we divide both sides by 3. So we get tangent x is equal to 1/3. And then getting the square root of both sides, so tangent x must be equal to plus or minus square root of 3 all over 3. So here we have two possibilities. Your tangent x must be equal to positive square root of 3 over 3, or your tangent x must be equal to negative square root of 3 all over 3. So continuing the solution, if tangent x is square root of 3 over 3, again, this is positive, so it's greater than 0, then x must be in the first or in the third quadrant. All right? And the reference angle for this one, remember, tangent is equal to square root of 3 over 3 whenever your angle is pi over 6. Okay, that's our reference angle. So we have pi over 6 in the first quadrant, and to get the angle in the third quadrant, that is just pi plus the reference angle. So we get pi plus pi over 6. So that's 7 pi over 6. Okay, so now if tangent x is negative square root of 3 over 3, again, if your tangent is negative, you're in the second or in the fourth quadrant. So again, we already know from the previous example that our reference angle is pi over 6. So to get the answer in the second quadrant, that's pi minus pi over 6. So we get 5 pi over 6. And in the fourth quadrant, the formula would be 2 pi minus the reference. So 2 pi minus pi over 6, we get 11 pi over 6. So thus, our solution set, or fundamental solution set rather, is the set containing pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. All right, so I hope that is clear. So again, if we wish to get the solution set, we just have to add 2 pi n to every single element, and do not forget the condition that n is an integer. Let's have example 7. So solve for the fundamental solution set of cosine x minus tangent x equals 0. So with this, since we know that we can write tangent in terms of cosine, all we need to do is to change tangent using the ratio or the quotient identity. So tangent is just sine x over cosine x. And then what we do next is to multiply everything by cosine x. So this now becomes cosine squared x minus sine x equals 0. So but still, we have two different trigonometric functions involved. So we change one of them in terms of the other. But I think it's easier to change cosine squared in terms of sine using again our Pythagorean identity. Cosine squared x is just 1 minus sine squared x. Then minus sine x equals 0. So we see here that our equation is actually quadratic in form. So by just rearranging in descending exponents, we're going to have sine squared x plus sine x minus 1 equals 0. So what we did here is that after rearranging negative sine squared x minus sine x plus 1 equals 0, we divided both sides by negative 1 so that everything will just be positive and it will be easier to solve. So from this one, let's see how this will be done. So this is the simplified form already. So now we'll try to solve this one. So we let u to be equal to sine x. All right. So if we let u to be sine x, then we can rewrite the entire expression as u squared plus u minus 1 equals 0. And now this is easier to solve. Okay. So since this is not factorable, we're using our quadratic formula here. So u would be, again, the quadratic formula is negative b plus minus square root of b squared minus 4ac all over 2a. So a here is 1, b is 1, c is negative 1. So we have negative b, so we have negative 1 plus or minus square root of b squared. So we have 1 squared minus 4 times a, which is 1, times c, which is negative 1, all over 2 times a. So a is negative 1. So simplifying this, we will arrive with negative 1 plus minus square root of 5 all over 2. So by substituting it back, we have sine x equals negative 1 plus or minus square root of 5 all over 2. So that means we have two possible equations. We have sine x equals negative 1 plus square root of 5 all over 2, or sine x equals negative 1 minus square root of 5 all over 2. So let's look at the following. So since sine x is equal to negative 1 plus square root of 5 all over 2. So take note that square root of 5 is in between square root of 4 and square root of 9. So that means square root of 5 is more than 2 but less than 3. So if a number is more than 2, if you subtract by 1, then the answer is still positive. So that means our numerator is positive. And if we divide that by 2, okay, that means our answer is what? Is still positive. Okay? So meaning this one is greater than 0. Okay? And we're also sure that this is less than 1. Why is it important for us to know that it is less than 1? If it's positive, Why is it important for us to know that it is less than 1? Because again, the range of sign is from -1 to 1. So meaning, if this value is greater than 1, then it is not possible to happen. Because your sign value, your sign x must only have a value at most 1. Alright? So why are we sure that this is less than 1? Again, take note, your square root of 5 is more than 2 but less than 3. Okay? So if this is more than 2 but less than 3, we subtract it by 1, then we're sure that this value, your numerator rather, must be more than 1. Okay? More than 1 but less than 2. Remember, I hope you can follow. So just imagine the lower limit of square root of 5 is 2. Okay? And then its upper limit is 3. Because square root of 5 is in between 2 and 3. So if you subtract 2 minus 1, that is 1. And then 3 minus 1 is 2. So that means the value of -1 plus square root of 5 is between 1 and 2. So if we have a number between 1 and 2, and we divide that by 2, then that means our number is in between 1/2 and 1. Okay? Our number must be between 1/2 and 1. That's why we are sure that this value is less than -1. I'm rather less than 1. Okay? So it means it's within the range of sign. So then that means the value of x in the first quadrant must be arcsine of this value, -1 plus square root of 5 all over 2. Okay, so we're sure that this is in the first quadrant again because it is positive. So now that we know this, we have to check other than the first quadrant, where is sign positive? Where is sign greater than 0 or positive? We have the second quadrant. And how do we get the angle in the second quadrant? It's pi minus the reference angle. But the reference angle, but take note, di ba, that the angle in the first quadrant is already our reference angle. So that's why our second solution or other solution is pi minus arcsine of -1 plus square root of 5 all over 2. So this is our angle in the second quadrant. Okay? So we're done with the plus part. Now let's look at the next solution. Okay? So if sine x is equal to -1 minus square root of 5 all over 2, so this is negative. We're sure about that because if we um have a negative value subtracted by another, wait, that would be confusing. So if you have a negative value and you're adding another negative value, then the answer must be negative. So the numerator is always negative, and then our denominator is positive. So if we divide a negative number by a positive number, then it must be negative. So it should be less than 0. However, take note that if we add -1 and negative square root of 5, our answer will be less than -1. Why is that so? So again, just like with our argument a while ago, square root of 5 is in between 2 and 3. Okay? So that means if we use the 2 and 3 as our limits, upper bound or lower bound of our interval, so -1 minus -2, that's -3, divided by 2, so that's -3/2. Okay? And then for the upper bound, if we use 3, so -1 minus 3 is -4, over 2, it's -2. So that means that this value negative 1 minus square root of 5 all over 2 is in between negative 2 and negative 3 halves. But we know that, so that means if it's in between negative 2 and negative 3 halves, it must be less than negative 1. But take note again that the range of sine x is from negative 1 to 1 only. Anything outside of that can't be a value of sine x. So that means your sine x here, because 1 minus negative 1 minus square root of 5 all over 2 is less than negative 1, then this value is an impossible value for sine because it's less than negative 1. So therefore, there is no solution for x in this second possible value. All right? So with that, our fundamental solution set will only contain arc sine of negative 1 plus square root of 5 over 2 and pi minus arc sine of negative 1 plus square root of 5 all over 2. So let's, you may try to answer these two questions. You may pause the video first and then later on, you may check the solution. All right. So now we try to answer this. So for number 1, solution. So we do is to first change sine squared x in terms of cosine using your Pythagorean identity. So we can change this to 1 minus cosine squared x. Okay? So again, your sine squared x is just is equal to 1 minus cosine squared x using Pythagorean identity. Next, we can now simplify. So basically, we just have, so let's just fix this. So 1 minus cosine squared x minus cosine x, and then 1 plus 1 is just 2. Right? So 1 here and 1 there. We can just combine them. So we get this. And then what we'll do is to divide everything by negative 1. So we may avoid the negative signs for cosine squared. So negative cosine squared divided by negative 1 is cosine squared. Negative cosine x divided by negative 1 is positive cosine x. And then positive 2 divided by negative 1 is negative 2. So we have this one. So the next step is to let u to be equal to cosine x. So if we do this, what will happen? So our equation now, or this entire thing, can now be written as, if we change cosine, so that becomes u squared plus u minus 2 equals 0. All right? So let's now try to simplify that. So let's just raise this above, just in case our solution it will be quite long. All right? So now let's try to solve this. So this is also not, is this factorable? So I think it is. So this is just u plus 2 and u minus 1 equals 0. Right? Is that correct? So we have, using FOL, u times u is u squared, and then negative u plus 2u will be u, and then 2 times negative 1 is negative 2. Okay? So that's the correct factor. So it follows from here that u plus 2 must be equal to 0, or u minus 1 must be equal to 0. So if we solve this, so for the first one, u must be equal to negative 2, or u must be equal to 1. Okay. So, but what is u again? U is cosine x. So, we change u to cosine x. Okay. And then for the other one, we change this. Oops. So again, we change u to cosine x. Or, right? Okay. So from here, just like what we did on the previous example, remember that the range of cosine is from negative 1 to 1, meaning it cannot have a value that is equal to anything less than negative 1 or more than 1. But negative 2 is clearly less than negative 1. Okay, it's clearly less than negative 1. So that means that for the first part, x doesn't have a solution. Okay, so again, for the first one, x does not have a solution, or you can use, oh, I forgot the symbol. Let's just use this. Okay, x doesn't have a solution for the first one, again, because negative 2 is outside the range of cosine. And then for the second one, we know that cosine is equal to 1 if we are in the positive x-axis. So that means x must be equal to 0. All right. So it means, based here, our fundamental solution set only contains one solution, and that solution is the set containing 0. Okay. And if we wish to get the solution set, to get the solution set, so that is just 0 plus 2 pi n, or simply you can just write 2 pi n because adding 0 doesn't change a thing, no? Where n is an integer. All right? I hope that is clear. So now let's try the last one. So for this one, again, we will just use our Pythagorean identity. So we want to change cotangent squared in terms of cosecant, and we can do that by changing cotangent into cosecant squared. Squared. Oops. Yan. Squared theta minus 1. And remember that cosecant squared theta is equal to cotangent squared plus 1. So changing cotangent squared with its equivalent, so we get this. And then we just simplify everything. So we're going to get negative cosecant squared theta. Okay, so we distribute. And then plus cosecant theta, and then we get sorry for my voice. So negative 1, so negative being distributed, so negative 1 times negative 1, positive 1, and then plus 1, we get plus 2 equals 0. Okay, so again, just to avoid the negative, we will just divide everything by negative 1. So if we do that, so this becomes positive, this becomes negative, this also becomes negative. Okay, so just like what we did in the last example, so we let u to be equal to cosecant theta. And by doing that, this entire expression, okay, becomes u squared minus u minus 2 equals 0. And this is very much similar with the previous example or previous try exercise. So let's just do that. So again, this is factorable, but this time around, the factors are u minus 2 and u plus 1 equals 0. So let's check. So u times u is u squared. U times 1 is u. Negative 2 times u is negative 2u plus u is negative u. The negative 2 times positive 1 is negative 2. So with this, we know that u minus 2 must be equal to 0, or u plus 1 equals 0. So solving for the value of u, we now know that u is equal to 2, or u is equal to negative 1. But by substituting, we know that u is cosecant theta. So let's just copy the entire thing. And then we replace u with cosecant theta. So we have this. Okay. Just to make it easier for us to solve or to remember, we know that cosecant again is the reciprocal of sine. So let's just use the sine function. So if we change cosecant to sine, then we need to get the reciprocal of their values. So the reciprocal of 2 is 1/2. Or, again, if we change cosecant to sine, the reciprocal of negative 1 is still negative 1. Okay? So we have this. So with this, I think it's easier to solve. So for the first one, so when is sine equal to 1/2? So again, it's positive. So in the first quadrant, so that means our answer must be in the first quadrant or in the second quadrant. In the first quadrant, so we know that our answer is pi over 6. And in the second quadrant, we've done this a lot of times in the previous example. So we know that the other answer in the second quadrant is 5 pi over 6. And then for the second example, or the second part of the solution rather, so when is sine equal to negative 1? So it's equal to negative 1 when we are in the negative y-axis. So that must be 3 pi over 2. All right? So that means our solution, or our FSS rather, our FSS would be the set containing pi over 6 5 pi over 6 and 3 pi over. Okay. And for our solution set, in case you were asked to give the solution set, so again, all we need to do is to add 2n pi or 2 pi n. So plus 2 pi n. So let's just copy that to every element. Oops, not there. Control, wait. Okay, and then we just do not forget the condition that n is an integer. So let's just make it smaller so it will fit. Or probably this na lang. There. Okay? So that's the full solution for your try exercises. So on the next video, we will talk about the third solving tip for trigonometric equations.